and that heats up that area of the Earth more. If it comes in at an angle, it's spread out over a bigger area. Now that can be hard to picture. I have here to help you visualize that a bundle of spaghetti, which
That's a
represents
good
the
one.
rays from the sun. So you imagine each piece of spaghetti is a light ray coming from the sun. In the summertime, those light rays are coming very directly down onto the surface of the Earth. So if I draw a circle around the spaghetti now, here on the Earth's surface, I find that it makes pretty much a circle on the surface of the Earth. So the light rays come down directly onto the surface. Now I'm going to have the spaghetti come in at an angle to the Earth's surface. This is as it is in winter time. So now if I draw a circle around the spaghetti, I find that the area marked out is much larger than it was the first time. In fact, it's not even close to a circle. It's a big, elongated area on the Earth. So the sunlight in this
So basically, the same energy that comes from this chunk of spaghetti, if you could think each spaghetti as being something carrying energy, in the first case, in the summer, that energy is concentrated in an area that is smaller than it is in wintertime. So in the wintertime, that same energy now is spread out over a bigger area because the sun is casting light at a given angle. So let me see if it can be seen from the perspective of somebody living here on Earth. And I'm bringing to your consideration an animation. And this animation in the Starry Night software, and I will show you this basic difference in the sky as the result of Earth rotation, Earth revolution around the sun. That explains why we see different skies on different months of the year. And maybe we can explore precession. So this is a fake background, so it doesn't represent San Jose at all. But up here you can see. By the way, Mia, can you see my screen all right?
Yes, I
Okay.
can see.
So you have San Jose at 7/12, June 20. It's pretty much close to solstice, which is tomorrow, June 21st. Summer solstice, the longest day of the year. And so what is happening here is the time is changing 1 second every second, which means the sky it is shown as we would perceive if we were outside. I can, with the software, get rid of daylight, for instance. And then we have the night sky. Let me just make sure I have the proper setting. Just 1 second. I think my preferences are correct. That looks good. Okay. So it's 7:14. Of course, there is sun outside, but we pretend it's not. If the sun were not there, we would see all these stars. And what I would do now is to speed up the rate in which the time flowed. So instead of it being 1 second every second, I will allow that to go faster. And as it goes faster, you see this interesting aspect of the night sky, and that is, I mean, things happen to be rising. In other words, going from below horizon to above horizon in the eastern sky which is the part of the sky in your left hand side, right? And slowly but surely the stars rise and then reach maximum height as they cross due south. And I will show here a line called ecliptic line where the sun is always located. So the stars, they reach maximum height as they cross this line due south, and then they start going down, setting in the western sky. Why is this happening? So this is happening because Earth, in space, Earth rotates from the western sky to the eastern sky. So you have this eastern motion, and we call that prograde motion in the sky. And as a result, we see sky objects like those stars you're seeing in the simulation slowly drifting from the eastern sky or left hand side to the western sky, the right hand side. So I could speed up the time a little more, and then you can see the effects being quite dramatic. I can also add daylight. So now the part of the Earth hemisphere that we are in faces the sun, and then we experience daytime. So the sun rose in the eastern sky, the sun is going to be setting in the western sky, as you can see over there. And then once the sun is down, then the stars appear because now the atmosphere is not so bright anymore since the sun is not there anymore. And the sun will rise in the next day. So you see this moon, which is right here next to my hand tool. The moon also rose in the eastern sky and set in the western sky. So what is the result of this so-called daily or diurnal motion, which is the slowly rotation of Earth around its axis of rotation? So this diurnal motion or this apparent motion of stars, the sun and the moon, and the planets in the sky. Let me just bring on labels, the labels of planets and moon, and then you can see Jupiter rose in the eastern sky, and Jupiter will be setting in the western sky. The same thing with Saturn, rose in the eastern sky, is going to be set in the western sky. So planets, stars, and the sun and the moon, they all rise in the eastern sky. There's the moon over there, see that? And they will be in a time scale, a few hours later, 12 hours or so later, they will be setting in the western sky. So this is the first motion that you should understand as being factual in our solar system, and is the result of Earth spinning around its axis of rotation. Now, let me talk about the second major motion, and that's the one that gives rise to seasons. And for that, what I will do, I will bring the sun, I will stop all of this, and I will bring the sun to a time in the day that is pretty much noon, 12 p.m. There you go. So at 12 p.m., the sun is high up in the sky. The sun is not exactly due south, but it's close to due south. And here we are in June 25th. Let's bring it to June 21st, which is one of the solstices. And then what I would do, I would change the time scale to another day in the same time. So I'm going to go to one day later. See if I can do that. I think I can. It's funny, it's not allowing me to change anything. 12, 11, 10, 12, okay. Sorry, I didn't mean that. Something got frozen here. Try that again. Okay, that's there. Let's bring this to 12 o'clock, noon time, p.m. And well, I'm gonna change it right here since I can't go in there. So June 20, right? 21st. Where's the sun? Sun is right there. And let me just go over the time. Look at this, I'm changing the days quickly, right? Now I'm in August, September, and now I'm in October, October 8th. So at noon, what I'm trying to show here, November and December, somewhere around 20, the sun is in its lowest position in the sky. So if you look at the sun progression in the sky on December 21st, so this one, the sun's progression in the sky, it doesn't allow me to go faster. What happened with my software? If we observe this at 6 a.m., 6 a.m., or more 8 a.m., the sun is close to there you go. Past 9 a.m., the sun is pretty much rising in the eastern sky in December 21st, and it is rising very much close to due south. That is at 9 p.m., 9 a.m., I'm sorry. And then if we advance the time on December 21st to, let's say, 4 p.m., so in afternoon, we look towards the western sky and the sun is setting. So the sun rose close to the north, southeastern sky, and then it set in the southwestern sky, pretty much close to due south. So the number of hours we observe the sun above the horizon is not so much more than what, 8 hours or so. Not a lot, huh? But if you go to June 21st, which is gonna be pretty much our situation tomorrow. Tomorrow is solstice, and then we observe in the morning hours. If we go out and try to wait for the sun come up in the morning hours, so see that in the winter, in December 21st, the sun was up in the sky, what, 8 a.m., 9 a.m. But now 6, 7 a.m. is already above horizon. And then when it's going to be below horizon, you look in the western sky, it's going to be somewhere around 6 p.m. or so. So in the summertime, you have, in fact, in the summer solstice, you have the sun with longer number of hours or larger number of hours above horizon, so about 12 hours, depends on which latitude you live. But as you go to the winter solstice, the number of hours it stays above horizon is much less. So it's 8 or 7 hours, and all depends on latitude. So more sunlight during daytime, more heat is accumulated on Earth. And less sunlight, you have less heat. And that explains one of the features of winter. Another feature is the sun close to your zenith itself. And for that, I will check the sun in June 21st at pretty much close to noontime. You have to look straight up in the sky, close to your zenith point, and zenith point is a point you define looking straight up, straight above your head. The sun is not so much far away from the zenith point, as you can see in this simulation. This circle in red represents the zenith point. Now let's do the same exercise not in June, but in December 21st. So in December 21st, the sun, where is the zenith? Zenith is there. See how far the sun is it is from zenith at noon? And on the contrary, the sun is pretty much close to your horizon, which means the sun rays are hitting you with an angle and spreading out that energy over a large surface area on Earth, which means, first of all, in the winter time, we have less sunlight during daytime. That's the main issue. The second issue is, even when the sun is above horizon, the amount of energy that is given to a square inch of any surface on Earth is much less than it is in the summertime. So you have less energy per square inch, and you have less sunlight during daytime. So seasons are caused by the fact that the Earth revolves around the sun, and also is due to the inclination of Earth's axis of rotation. Okay. And the third major motion is called precession, is a conic motion that is due to the fact that Earth's axis of rotation is inclined with respect to the orbital plane, first of all, and second, Earth has a bulging equatorial, an equatorial bulge, which is due to the fact that Earth spins and rotates and bulges up. And then both Moon and Sun exert gravitational tug on this bulge, and as a result of it, there is some external, as we use the word torque on Earth, and then Earth's axis of rotation precesses with a time scale of 26,000 years. What I would like to show now is an animation in that's further explore these three major motion. So you go to NAAP astronomy, just do a Google on it, and then you go to rotating sky. Oh my goodness, I have to update my computer. Not being able to run here. Probably I will try to do, oh, there you go, it's working. So in this animation, Earth is shown in the very center part of the celestial sphere. Again, celestial sphere is not a real thing, it's an imaginary sphere that was brought to the attention of ancient astronomers, as they thought that stars could be kind of glued to this sphere, and the sphere itself would rotate and would give this false perception that the stars are the one that goes around us and not us that rotates and then see the stars moving on an opposite direction. So here is the real situation as it goes in the sky. So the celestial sphere, if you bring stars on it, and bring a Big Dipper there. So the Big Dipper is not moving. As you see in the left-hand side animation, the Big Dipper is there. But because Earth rotates and because we are in a certain location on Earth, our perception is that, well, in respect to the floor, we are not moving. We are stationary. And what we see moving, in fact, is the sky. But the sky doesn't move. Well, in reality, it does. And we are going to learn in the future, in a few weeks from now, that everything in the universe is subjected to a motion, including stars. The stars have their own intrinsic motion, but they are so far away that we cannot detect their intrinsic motion. Like when you drive through the highway and look up to the mountain and you see a bunch of cows, even if they are moving, you don't perceive because their relative motion is so small compared to the distance we are from them that for us it appears they are not moving. Same thing with the stars that we see in the Big Dipper configuration. They all have their own intrinsic motion, but since they are so far away in our time scale of life, we think they are kind of in the same relative angular distance as we see here from Earth. So, so Earth rotates on its axis of rotation, and because of that, we see this display of stars. And if we add more stars, things get even better defined. Okay, so this animation is good to explore to further understand this situation. This is a simulation of the sun. It's kind of the same as before, but it shows the sun going in the sky, rising the eastern sky, as you can see here, reaching maximum height as it crosses due sight and going below horizon in the western sky. Now, as you can see, the dates are changing and the months are changing too. Now we are in May. So let me stop this and do a little tricky thing. I'm gonna put the sun right here at noon, as I did it before in my previous simulation, but I'm gonna place the marker on on June 21st, somewhere in June 21st. So that's when the sun is in the sky, closest to what we call the zenith point, which the point is straight up that you define as looking straight up. So as I move the months towards December, see that at noontime the sun approaches more and more the horizon up to when December 21st it reaches solstice. So if I keep advancing December, the sun will move up towards equinox in March 21st, and then summer in June 21st. Why is that? Well, the reason for this apparent motion of the sun in the sky at noon, this is all shown at the time of the day that is noon. I put 11:57, but it's pretty much noon. Let me put that at noon. There you go, noon. Right when the sun crosses the meridian. And the latitude, I put 47, but San Jose is 37. That's a good one. Okay, there you go. And this is caused because the Earth revolves around the sun. So let me see if I have a animation that shows Earth rotating around the sun and giving rise to this different. I don't think I do. Basic coordinating system. This could be a good one. Let me see. There you go. So here's the sun and Earth. Earth has its axis of rotation fixed, and here are the months. Here are the months of the year, right? February, March. See, the axis of rotations are always pointing the same direction. They don't change it. But when you get an equinox in March 21st, so both north and southern hemisphere they both receive the same illumination, and that's what you can see in this animation over here, right? Now, as you advance towards the summer solstice in the northern hemisphere, see this little dude over here. So the sun appears to be going to a position that is pretty much close to, right here, it's pretty much close to the zenith point, right? That's when they have more energy spread over a small area, over a given area on Earth. This reminds me of the spaghettis we just saw. And if the animation keep on going, then again, we are going to experience on Earth another equinox, that is the fall equinox in the northern hemisphere in September 21st, when now the northern hemisphere you start to experience winter time, and the southern hemisphere will experience summer solstice. Okay. So these three animations I would like you to explore as you have the opportunity to, and what I will do tomorrow is to upload in our Canvas course the PowerPoint of this chapter 2, which I just realized is not there for some reason, and then you can better follow this PowerPoint. Okay. So do you have any question you want to ask?
No, that was very helpful. Thank you.
Okay. All right. Email me again if you have any question, and this is being taped. I will upload in a second, and tomorrow I will go over the PowerPoints again of chapter 2. Chapter 2 is a long chapter, and I think that's why I have it gone for more than one day. So we'll still be exploring chapter 2 tomorrow, and more particularly, I will be talking about moons and the moon's phase. Okay?
Okay.
Okay. See you mañana.
Thank you.
Okay, bye.